Hello everybody. Now I will start with the new module of mathematical modeling of manufacturing processes. So this is little bit in different aspect, not exactly the modeling of this thing, but rather more on that micro or nanoscale manufacturing processes. We will try to get some overview of the different types of the micro scale or nanoscale manufacturing processes, but this overview mainly focused on the joining or assembly of these two components. In that part I will try to focus here. So, of course, in this micro or nanoscale manufacturing, most of the cases we start with the downscaling of the conventional processes, and of course, that sometimes it is necessary to integrate the different length scale of the component. So, therefore, the fabrication techniques for the in different micro or nanoscale processes, and apart from that, the different manufacturing processes relevant to the packaging, finishing processes, micro joining and nano joining, micro casting, micro forming, and of course, micro machining. All these aspects I will try to look into just to overview of these topics. Now, if you see that microsystem technology, and that brings the possibilities of integrating the functionality or different multi-material, and of course, it try to bring some intelligence in the when you try to make some devices which is in micro scale or maybe nano scale devices. So, in that case, so actually most of the development in the micro scale normally confined to the semiconductor industries, and last 2 decades there are so many developments happens in this area. And of course, this apart from the semiconductor technology, and that is mostly applicated in the integrated circuit, and these are the prime focused in the last 2 decades of microsystem technologies. But of course, apart from that, microsystem technology can also be applicable on engineering technologies. For example, by using the milling process, so electro discharge machining, electrochemical machining, laser ablation, drilling and turning, and the different scale where we can have possible to obtain different surface finish by using this type of different manufacturing technologies. So, but nowadays with the development of the new materials, and of course, more complicated geometry, and of course, if with the reduction of the size of the components. So, therefore, new technologies has been developed, or maybe hybrid technology has been developed that is related to the microsystem technology. So, we will try to look into that different manufacturing process, how we can bring from conventional processes to the micro scale processes. So, therefore, in these cases new processing technology therefore must be capable to produce some miniature products, and of course, with the intelligent different multi-material mix and creating some interface such that it is possible to assemble the different component, and of course, for particular achieving some particular function at the same time at different length scale. So, if we see that most of MST, that means microsystem technology, actually faces the difficulty when you try to reduce from conventional manufacturing process to this micro scale manufacturing processes, or maybe you can downscaling the processes. Maybe sometimes it is not possible to proportionate way the vary the force components, and of course, these components of the force depend on the size of the components. So, there may be some reduction in the force component may be necessary when you are downscaling the conventional processes. So, therefore, new manufacturing processes try to utilize some different types of the mechanism of the particular material, developed material, for example, magnetic. So, rather controlling of the force using some magnetic material, piezoelectric material, of course, ferroelectric and safe memory, such that it is possible to control the force very accurately, and at the same time some controlling of all these different kind of forces, and then with the particular reaction time. So, that is also important in the microsystem technology. So, using all these different new developed materials, the development of the new technology is going on in the specific to application in the or to produce some kind of micro devices or nano devices. Of course, if we look into the different surface micro machining processes, there is a wide varieties of processes available. For example, micro electro discharge machining, micro electrochemical machining, micro milling, ultraviolet lithography, electroforming, and the laser ablation. by combining with the batch fabrication methods like micro injection molding, embossing, imprinting and coining to produce high aspect ratio structures in metals, plastics and ceramics. So, all this we can find out the application in any kind of the microsystem technology using all this kind of materials. But of course, integration of the various functions of the products is the main part of the microsystem technology, and that is the job of a development, or that is the drive for the development of the new manufacturing methods, such that it is possible to incorporate different length scale features. So, that is a more challenging task also in microsystem technology processes, and of course, it is also necessary the basic understanding of the different multi-material components, their responses, and of course, that is necessary what we can integrate the different component to produce one device. So, therefore, for example, the polymer based lab on chip platform, they actually aim integrating the active optical components like planar surface plasmon resonance sensor with the microfluidic system. So, when you try to look into this integration of this resonance sensors with the microfluidic system, then it becomes challenging in a micro devices, and of course, here we necessary to actually handle the different types of the material and what we can interact with respect to different material, that is also typical difficulties in case of microsystem technology. Even if we look into the lab on chip device involves the functionalities of the microfluidic channels, involve the reservoirs, valves, pumps, or are integrated microprocessor, all are integrated to very small component even to achieve high sensitivity and having the individual load, very analysis speed, very low sample consumption and measurement automation, all are actually involved and in case of lab on chip device. So, therefore, this is the small device. If you try to look into that, then we need to know the mechanism of the different components we have utilized here when we are interacting with this or all these different components and their response with the in this component. So, that is also important for analyze, and in general for another example we can look into the contact lens, sum of a micro scale metal interconnects in a bicompatible polymer that includes light emitting diodes also, that way contact lens, and that this understanding of this mechanism so opens up the new idea of the development of the new technology as well. So, in that sense we need to understand that different mechanism, which mechanism is responsible apart from this their manufacturing of all these components. So, even if you look into that different group of mechanical and energy assisted that normally used in a microsystem technology, for example, micro machining, different micro milling, diamond machining, that can also be used. So, therefore, even apart from that is the mechanical finishing process, machining process, apart from that energy assisted process. So, for example, electro discharge, electrochemical, electron beam, ion beam machining and ultra short pulse laser ablation. This all these cases it is possible to control, it is a very minute material removal, or maybe affected zone may be very small, all these cases when you try to develop from conventional to the micro scale component. And of course, this what extent we can use is this, it depends on the which we have to look into that length scale of this component we are supposed to use. So, therefore, all these mechanical and energy assisted processes we assemble together, it is possible that could provide the 3-dimensional necessary structure, taking the advantage of all the different types of the manufacturing processes. And of course, all these processes can also be applicable for a wide range of material. For example, one process may be applicable for the metallic material and at the same time that it may not be applicable for the non-metallic material. So, therefore, wide range of materials coverage are there. If a group of mechanical, or if we know that each are individual manufacturing processes and their response in the when you try to downscaling of these processes. So, therefore, typically the materials machines by these processes are the same as those used in the macro manufacturing, but of course, same method, same principle we use it, but of course, in the micro manufacturing cases all that we normally downscales the conventional processes. For example, to perform structuring at the given processing window, different material removal mechanism we need to understand, and which is responsible for structuring of the structuring at different scales. So, therefore, but if we look into the mechanical assisted and energy assisted processes, basically finishing processes we can say, or machining processes we can say. So, in these cases the energy assisted process is more suitable than mechanical processes, or more accurately we can utilize these things. And of course, this non-conventional, for example, electrochemical machining is more applicable to even for the wide range of the materials as compared to the conventional processes. So, therefore, some development happens in that particular area. So, but if we look at that two specific parameters, we can decide that this microsystem technology, one is the specific processing energy what are you using, and second is the material removal techniques, and what type of material removal techniques we can look into, just different, and of course, and the different processes or different length scale, the amount of the energy, specific energy requirement will be different for these cases. So, therefore, then if we know this parameters range, it is possible to integrate the manufacturing of a component having two different length scale. Now, I am going back, not exactly going back to, but rather I am trying to focus on this one of the micro manufacturing technology that we just that is called the micro or nano joining processes, or sometimes we call in say micro nano welding processes. So, we just try to look into the what are the different developments happens in case of the micro or nano joining processes. So, it is of course, it is one of the manufacturing process, basic manufacturing processes apart from machining, casting and forming and finishing, all their development also happens, all this conventional manufacturing process at the micro scale. Now, if we look into that micro scale or nanoscale joining processes, of course, in these cases it is required in microsystem technology the handling of the both metallic material and non-metallic materials, and of course, the handling should be in a relatively smaller scale. So, it is a simply downscaling of the conventional welding processes we can develop the micro or nano joining technologies. Of course, more precisely it can goes to the nano welding technology or nano joining technologies, but in general the difference from the conventional processes is that what we can control the heat source. So, intensity of the heat and the amount of the heat flux we apply to the substrate for any kind of the processing or joining processes. So, controlling of this is the main features for the development of the micro or nanoscale joining process. If we look into the mechanism of the basic mechanism of the metal joining or welding processes, it is like that if two surfaces are perfectly flat and they are atomically flat of course and perfectly clean, then if we bring together these two surfaces, they actually spontaneously joining by interatomic forces, but we have to prepare this kind of surface. So, normally presence of the some surface in the in a particular component that actually holds some large amount of the Gibbs free energy. So, if it is possible to reduce the Gibbs free energy by removing the high energy surfaces to low energy interfaces, if we create that kind of the situation, then two surfaces can be joined more easily. But in general, if you see the most of the engineering surface is contaminated in the form of the oxides layer or some other, or either contaminated in the, or there is a rough surfaces, if that rough surface may be, if we look into the micro scale. So, therefore, some sort of energy is required to remove these oxides layers, and of course, in the most of the cases we put this heat, can be directly applying the heat or some frictional heat or with the application of the pressure, such that to remove these impurities exist over the surface and they bring the contact or may bring these two surfaces in contact, that helps to join between these two components. So, therefore, in principle some amount of the energy is required if you want to join these two surfaces, and these surfaces characterize these two things. One is the minimization of the Gibbs free energy of the surface, and second one is it should be atomically, try to bring in that situation, it should be atomically flat. So, in that cases it can easily be joined, these two components. So, based on the physical states of the parts to be joined, actually in the all these four category, fusion welding, solid state welding, soldering, brazing and adhesive bonding, all these cases there is a development of the micro welding is done. Now, in general, if we look in the microwelding, suppose most convenient way for the development of the microwelding processes from conventional to that microwelding simply downscaling, apart from the increasing the decreasing the intensity, that it can be done from continuous mode to pulse mode, because it in pulse mode it is possible to control the energy supplied to the substrate material, and of course, that is why pulse laser is most suitable, and most of the development of the microwelding system has been done based on the using the pulse welding process. So, apart from using the low power intensity laser. So, therefore, techniques for microwelding it with similarly control variables such as voltage, current and double speed in case of microwelding processes. It can be continuous or pulse mode, even continuous mode, then definitely continuous mode we not have much option, because in this case only the reduction of the power or intensity is the possible, but when you try to look into pulse mode, there is a looking into the pulse modulation strategy, we can vary the intensity of the power. So, therefore, or maybe we can reduce the average laser power, which is average laser power it is to some extent equivalent to the continuous mode of laser. And of course, not only laser also, this reduction of the pulse or mode is also available even for arc welding processes also. So, therefore, in general that microwelding system is can be developed to looking into that influence of the or either continuous mode or more effectively from the pulse mode of operation. So, if we look that in microwelding system, this mainly 4 resistance: arc welding, TIG, MIG and plasma and laser. The development happens in the microwelding system. Apart from that, also electron beam welding could be considered for the miniature welding process. So, we will try to discuss this at basics things of development of the different micro scale welding processes. Now, fusion microwelding, of course, fusion microwelding the processing can be done by heating the material above the melting point temperature, then we allow the solidification for a particular material, metallic material, and then after solidification we can get the structure. Of course, when you look handling the microwelding or telling the microwelding system, the material volume maybe handling is very small in these cases as compared to the conventional processes, and of course, thickness may be restricted to less than 500 micrometer of a particular component. We can say it is a kind of microwelding process, but microwelding development has been done even in arc welding processes, but with a presence of the regulated and controlled outputs of less than 1 amp, and that is possible even for GTA TIG welding processes. It is possible to use in the pulse mode, even for plasma arc welding process it is possible to use in the pulse mode. So, they can be used in the microwelding application. So, mainly the development happens in GT and plasma microwelding processes, and peak pulse controls the penetration. So, intensity controls the peak pulse, that means what is the peak power controls the penetration, and of course, background or base current sometimes allows the solidification without extinguish the arc. So, that is the main features in arc welding processes. If we look into the power beam welding processes, both the laser and electron beam welding process is mostly developed in the microwelding application. In this case, very fine control over power and positioning is possible, and that is why we use mostly the very precision microwelding application. The laser and electron beam is the most suitable source, and as compared to the arc welding processes, of course. And it is a focus, because laser can be or electron can be focused into a very small area onto say also maybe limited heat effector zone can be produced using the laser. So, that can be one advantages to develop the microwelding processes. And of course, deep penetration can also process, because high intensity laser can be used, and with that little distortion can be controlled even if you use the laser also. But electron beam welding process, all the process has been performed under the vacuum. And of course, laser beam welding normally we can use the kind of inert gas atmosphere. And of course, this electron beam or laser beam welding process having advantages or in development of the micro welding system, but of course, in terms of the cost, this electron beam or laser beam micro welding process is little bit costly as compared to the arc welding process. But till the development also have done in arc welding process, what if you want to look into very small very precision welding process, even its accuracy level may be very small, even length scale is very small. So, in that case probably the laser or electron beam welding is the most suitable processes for the development of the micro welding system. So, laser beam energy down to the order of the 10 of a micron, that can also be possible, and even laser energy, that pulse, basically pulsation reduce the thermal input as well as the reduce the distortion. That is the advantage of using the pulse laser mode in micro welding processes. So, apart from that, some solid state bonding also developed in the, that is in the category of the micro welding or micro joining processes. So, of course, in this solid state bonding process no melting happens, joints are made and the plastic deformation at the interface and intimate contact, and finally from a bond. Of course, sometimes it creates some kind of the morphology such that they after plasticization they create some interlock in the surfaces from one surface to the another surface. And in this case micro joining processes normally in the solid state ultrasonic vibration or friction welding and diffusion bonding, these are the main development, and either in the liquid or the solid phase, these are the most suitable processes in solid state bonding processes. Friction welding in this case is the friction heat generation by the friction, heat actually generated because of the friction and with the application of the pressure and extraction stirring of the materials. And even nowadays the development of the friction state welding also happen and at the micro scale. And in this case solid state bonding process is mostly suitable wide range of materials, and of course apart from that non-metals cannot be used here, and dissimilar combination is more advantageous with the application of the solid state bonding processes, because dissimilar welding process melting of the, when you try to fusion welding will be applied for the dissimilar joining process, most of the cases it creates some kind of the intermetallics, and which may be brittle intermetallic deteriorate the joint strength, the life of the welded joint. So, in that sense solid state bonding is for dissimilar metal combination is more suitable. So, that is why some development happens in the solid state bonding process. But one limitation in friction welding is geometry should be symmetric in nature and preferably used for joining components to heat sink. In case of electronics industry, we can get the application, the joining of the heat sinks in the electronics industry, one of the more practical application of the solid state bonding process or friction welding processes. We can example aluminum heat sinks to aluminum substrate we will try to join. The friction welding is one of the suitable method here. So, most commonly used for attaching tubes or rods to a bulk sheet, we normally follow kind of the friction welding process, even it is in the micro scale. Ultrasonic bonding is another type of the solid state bonding process. In this case the ultrasonic vibration we create here through displacement of the intermetallic oxides or a contaminated layer removes by using the pressure to form a bond. So, normally high frequency vibration along with the low pressure is responsible to cause the plastic deformation, and this can be applied in very localized space. So, in the localized area sometimes even we use the ultrasonic source for the microstructure modification also. So, definitely since it is confined, it is a very small zone and small rise in the temperature in this solid state bonding process. So, it is mostly used in case of plastics and especially for joining of the dissimilar materials. Most significant process in electronics industry, we can use this ultrasonic bonding process, choice in case of thermally sensitive material. So, thermally sensitive materials, that is in that cases the ultrasonic is the most suitable process, ultrasonic bonding, and in these cases bonding force can be much lower compared to the thermocompression bonding other cases, and it is advantageous if the materials susceptible to deformation or try to form the crack. So, that type of material is more suitable with the application of the ultrasonic bonding process. Solid state bonding, if you see in solid state bonding, one is the diffusion bonding. The principle of the solid state diffusion is the atoms of the two solid phases when come in metallic interfaces come in interact with respect to each other, and that is required to hold for a sufficient time such that allow a diffusion occurs between the two layers. But of course, in these cases the diffusion is aided by the diffusion can be accelerated by application of the small amount of the heat. So, around 50% to 70% of the melting point temperature along with the pressure for a period of time. So, now two things are important here in the solid state bonding process. The asperities we are in contact, that is also physically deformed with respect to each other. So, that asperities is one important aspect, and apart from that the removal of the oxides layer, what we can remove the oxides layer such that intimate contact between the two surfaces may happen in these cases. So, when asperities of the two surfaces contact and physically interlock with respect to due to the plastic deformation. So, in these cases it is forming the interfaces between the two surfaces by plastic deformation, and it is very very localized area it is possible to do the diffusion, and this diffusion is not mostly not associated with the change in temperature. So, therefore, minimal distortion to the components happens. So, prior to welding, the surface preparation is one of the important aspects for to get the successful diffusion welding of the components. So, as minimum as possible to remove the contaminated layer from the surfaces, then diffusion welding becomes more successful. And smooth surface finish, economically viable and kept as free from chemical contamination as possible, that is a more important aspect in case of the diffusion bonding process. Now, one of the application of this diffusion bonding, solid state bonding of the microelectronics wire bonding, we can get the application of the microelectronics wire bonding. So, basically joining between an integrated circuit to a semiconductor device. So, when bonding is the most cost effective and most flexible interconnect technology normally happens, and if properly designed bonding, it is a high speed bonding can be done at a very high frequency, the order of gigahertz. But principle of the joining these components bonding is basically ultrasonic welding process. Sometimes this ultrasonic welding process added by the some kind of the heat. So, that is called the thermosonic bonding process. So, in this case bond head oscillates at the ultrasonic frequencies and scrubbing the two metals together and form a weld. So, therefore, the bonders are capable of making a bond almost every half second, that means this is a very fast process. And brings process description, we can see the brings the two materials together to be bonded using pressure as well as the ultrasonic energy. If we apply both together, then that is called the heat, pressure and energy, all three we can apply together, then it is called referred to as the thermosonic bonding process. Even bonding can also be processing using nanoparticles. We know that nanoparticles normally the size of these nanoparticles is in between 1 to 100 nanometer. So, in these cases the properties of this size less than 100 nanometer particles is completely different from the conventional particles which is size is bigger, and because the main aspect is the volume by area ratio is very much high in case of the nanoparticles. So, the properties actually depends on this volume by area ratio, higher surface area to the volume ratio. So, in this case, so that is the huge differences between the size of the particle. If you reduce the size of the particles, there is a difference in the surface area to volume. So, therefore, nano size particles when come together, the contact areas are stressed between these together and them increasing significantly. So, when two interfaces is filled with the nanoparticles, when you apply the pressure, so basically surface area increases significantly. So, large surface area of the nanoparticles affects the surface atom of the bulk metals. So, therefore, a metal to metal bonding is more strong with the using of the nanoparticles, and they act simply as a filler materials. So, therefore, may achieved at significantly lower. So, this kind of joining may also achieve significantly lower bonding temperature than fusion welding and diffusion bonding process. If you see bonding using nanoparticles, that composite silver consists of the silver metallo-organic nanoparticles and Ag2CO3 particles. If we look into these are the typical nanoparticles we use, and if we look into that between these two components from the figure, the layer of the nanoparticles is basically filled between these two components, and we simply apply the pressure. So, therefore, joining of the various metals can be done, for example, silver, gold, copper, nickel, titanium, aluminum, all can be joined, and the more important part is the temperature, and the holding time is the one important parameter to get the bonding strength. So, herefore, Sintering of the nanoparticles between each metal with the application of the temperature, and of course, it will be holding for a sufficient time. But if we look into that effectiveness of this joint, it depends on the what type of materials we are using. So, because the decomposition of oxide films is needed. So, initially the surface maybe some oxide layers are there. So, we need to remove to activate the metallurgical bonding. So, using the activate the nanoparticles between the two surfaces. So, the workpiece surfaces the oxide layer has to be removed first, such that then directly the nanoparticles come in contact with the actual metal. So, then it will be more easier to bond between these two components. Now, based on the shear strength of the joints, the bondability of the each metal can also be ranked in this way. For example, the maximum bondability is for silver, then copper, then nickel, then titanium and alloy, and actually identical to the order of the free energy value of the oxide formation. So, if we see the free energy value of the oxide formations, oxide layer formation are different for these things, and if we look into, if we rank it, it is the similar rank here we have already mentioned in these cases. So, in this case what happens, the reaction normally happens that produce normally CO or CO2, carbon monoxide and carbon dioxide. So, in this case the joint strength for copper, silver and gold are relatively good. If we see, they are in the copper, silver and gold, you can say these are relatively good, because the oxides are in these cases less stable and we can remove this oxide layer by reduced reaction. So, we can easily form this CO2 just to remove these oxides. So, in that cases bonding strength becomes more strong in these cases, but of course, the in case of aluminum and titanium, the it is very difficult to remove the oxide layer as compared to the copper and silver and gold. So, therefore, the oxides is more stable in case of aluminum, titanium. So, in that cases when you try to use the nanoparticles for bonding these two nickel or titanium or aluminum surfaces. So, in these cases we cannot produce that much of strength between these two components like silver and gold and copper. Now, we can look into the different types of the laser and which is used in the microwelding, or there is a development of the laser microwelding processes. One is the laser transmission welding. Actually, this laser transmission welding, it is possible to join two transparent material, but of course, this when we use the two transparent material, so laser is passes through the transparent material, but absorption should have been happened at the interface. So, in this case, if both materials having the similar transparent to the particular laser or wavelength of this laser we are using, in this case some absorbing medium should be there at the interface, such that it can absorb the laser energy, or energy will be released at the interface, and then at the interface the bonding can happen between these two components. So, this is the typical features of the laser transmission welding. Of course, one metal is transparent and another metal is not transparent. So, definitely we not necessary to use some kind of the absorbing medium at the interface. So, at the interface laser release the amount of the energy, laser energy, such that interface at the interface the bonding between the two components may happen. So, laser transmission welding is one of the application we can get in so many applications in the medical field, even in microwelding application. So, apart from that, ultra short pulse laser is one suitable source for the development of the different microwelding. Even more, actually the ultra short pulse laser process, ultra short pulse laser is normally used for the material ablation, is more established in this cases, but using the ultra short pulse laser that is established only for non-metallic material, but it is not well established in case of the metallic material joining the two components. But till there is a scope to development of this ultra short pulse laser welding process, specifically application in the micro welding, micro scale component. So, pulse duration in this cases, ultra short pulse duration is of the order of femtosecond to 10 picosecond, very short pulse as compared to the conventional laser pulse, because conventional laser pulse either micro milli second, and even for nanosecond pulse can also be produced, but when it goes to the order of the femtosecond to 10 picosecond, then we can say this is the ultra short pulse laser. The mechanism of the ultra short pulse laser is completely different as compared to the other conventional laser. In this case, the duration of the laser pulse is shorter than the time required for the energy to transfer to the surrounding area. So, that comparable with each other. So, therefore, absorption or material removal from the surface is completely different as compared to the other conventional processes. Now, application to short pulse laser, the medical application, for example, as replacement of mechanical drill in mechanical in dentistry. In the dentistry, we can get this application of this ultra short pulse laser, pattern carving in the wooden structure without leaving the behind burn traces. So, that we carve exactly, we can with producing the minimum amount of the heat affected zone or almost no heat affected zone. The material ablation can also be possible using the ultra short pulse laser. That is the advantage of using this laser. And of course, laser micro machining and ablation is applicable using the ultra short pulse laser. And in some cases we can, most of the non-metallic or metallic to non-metallic cases, we can find out the micro welding application using the ultra short pulse laser. And if you see this figure, the long pulse and femtosecond pulse, if you see the long pulse having some molten zone or vaporized zone depending upon the intensity of the laser, but in this case it creates little bit more the heat affected zone. But if you look into the femtosecond, that exactly the very small area and very controlled way we just remove the material, or at the same time it is possible to join the two components. But the pulse frequency is the one parameter that actually decides whether ablation mechanism is active or it is possible to change from ablation to the welding mechanism. So, if we look into long pulse laser, pulse duration is nanosecond or even greater than that. So, that pulse duration laser we normally call as a long pulse laser. Application area, medical application like skin treatment, also you can use micro welding, not macro welding processes. Cutting of the materials can also be used in using the long pulse laser. Now, there is some development even for the electron beam micro welding processes. So, in electron beam micro welding processes, it follow the scanning electron microscope principle. So, it is possible to develop the micro welding application for electron beam welding process just using the principle of the scanning electron microscope, or it is possible to convert scanning electron microscope to the electron beam micro welding process. So, what we can see that in SEM principle, you can see the analysis of the substrate, lowest possible energy input and the high resolution, that is the principle of the scanning electron microscope. But of course, in these cases there must be some electron source and we control in such a way such that the high resolution picture it is possible to capture in the observing mode. So, for this purpose some condenser lens is used, aperture is used, objective lens and the specimen. This is the typical structure of the scanning electron microscope. Here you see multiple apertures for screening of the off axis electrons. For that purpose we can use the multiple apertures, it is possible to use. Two condenser lens for the reduction of the excess electrons, that can be used, that is the purpose of the using the condenser lens. And finally, creates low power beam with extremely small focused spot on the sample. So, that is the principle of the scanning electron microscope, but this can be converted to the electron beam micro welding process. In this case, if you try to use this micro welding mode of this scanning electron microscope, what we can do? We can do the removal of the apertures, removal of the apertures and one condenser lens. If you remove it, then the structure can be modified like this. So, its focus length is increased here and condenser lens we just removed here and aperture we can remove here, and then we are simply getting the welding mode. So, in this case apertures actually reduce the effective beam power, and in this case modification reversible may be used as a both observing tool and as well as the welding. So, here 5 or 6 watt power can be generated from the from this scanning electron microscope. When you convert it, just removing some condenser lens and aperture, then it is possible to use as a welding mode such that 5 to 6 watt power can be produced. So, this micro electron beam in this way it is possible to develop the micro electron beam welding process. Even there is a development of the resistant micro welding process. So, we use the same principle in the resistant spot welding process. Here the heat generated by is mainly the electrical resistance, and when it passes through the current, high current through the electrode, and that with this very small duration, and that creates the hits the surfaces on the contact surfaces because of the contact resistance at the surfaces creates and that melt all these surfaces, but of course, the contact surface between the electrode and the workpiece is the heat generation will be minimum, because in this case at this contact the resistance is very small, and at the same time if you use the high conductive material as the electrode. So, even heat is generated at the interface between the electrode and the workpiece. So, heat will be immediately carried away by the high conductive electrode material. So, in conventional processes this high conductive electrode material normally use water cooled electrode, such that rate of the heat transfer can be effective when there is a heat generation between the electrode and the workpiece. We can easily estimate what is the amount of the heat generation by this using this equation H equal to I square RT. So, I is the applied current, R is the resistance, T is the time over which the current is applied. So, therefore, resistance R includes all the electrodes, sheets and contact surfaces, but the melting it happens the resistance between these two the two contact surfaces, or some constriction resistance must be there, because there is a flow of the current path and that depending on the what is the contact area at these surfaces. So, accordingly the heat generates at this contact surface. Now, resistance microwelding is actually simply downscaling of the conventional processes, but there is some difference between the large scale or conventional scale welding process with the micro resistant welding process. So, in these cases the large scale process the electrode pressure is much lower in a micro welding process, but if it is conventional process the electrode force is much higher. So, much lower electrode pressure results in the higher contact resistance. So, if force is very small, then its lacks of intimate contact between the contact surface. So, when there is a lack of intimate contact between the contact surfaces, that actually enhance the contact resistance. So, when there is a contact resistance is very high and the requirement of the welding current is less in these cases, and sometimes it promotes the electrode sticking to the workpiece. So, if you use the maximum nugget diameter is about 33% of the electrode diameter, chances of the electrode sticking is more in micro welding mode, since electrodes are not wire cooled. So, what are the heat is generated between the electrode and the workpiece in specifically in micro welding process. So, electrode size is very small. So, there is no scope to use some kind of the cooling system there. So, in that cases the heat transfer may not be effective as like the conventional process. So, there is sometimes in micro welding processes there is a chances for the development of the heat generation at the contact surface, and this mostly used for the non-ferrous metals and alloys such as copper, nickel, platinum, aluminum, all these kind of materials we normally use for the resistant micro welding process. But for regular welding process mostly or conventional welding process, conventional resistant spot welding process, mostly steel we normally use. Or sheets for micro welding often coated with the gold, silver, nickel, tin, so that having some influence of the heat transfer mechanism or surface quality also. But for regular we use normal, for regular means for conventional micro spot conventional resistant spot welding process we normally use the uncoated or coated sheet with the zinc, that is the more applicable in the automobile industry. Now, there are so many advancements in the laser micro welding process. One such advancement is called the shadow technique, which is stepless, high speed, accurate and discrete one pulse welding process. So, in these cases transforms the macro laser spot welder to a micro seam welder, and that is the main conversation or such that the development of the micro cell can be happen. So, maximum pulse length is normally happens in case of the diode laser. So, diode pump laser is mostly used for the development of the shadow technique, but in this technique if we look into that, and the figure 1 and figure 2 in these cases pulse mode, if you see that there is a pulse mode, the on and off of the laser pulse energy in this case. So, here on off mode there is, it so depends on the what is the overlapping of the pulse, and the shape is something like that. It is obvious from this figure also. Now, if you know what is the pulse duration of a particular laser, and within that duration if we cover the particular domain, then this one single pulse all energy will be deposited over this length. So, that is why this is possible if we move this supplied energy for the laser at a very high speed. So, within that high speed when try to move from one point to another within that high speed, so that it will cover within single pulse there is a coverage of the application of the pulse energy to the substrate material, and that creates kind of the single smooth surface as compared to the multiple overlapping surface what we normally observe in case of the spot welding process. So, that is the difference, and this is called the shadow technique, and this normally used for the welding of the watch component. That means shadow technique is mostly applicable in case of the metallic material. Other advances in the laser microweldings, for example, laser droplet welding, in this cases the overcome the gap bridging and highly reflective materials and high heat sensitive materials. So, in these cases when there is a gap between these two components, so to get successful joint between these two components having little bit more gap, and of course, in the at micro scale, then liquid metal droplet is created by using the end of the wire by the pulse laser, by application of the pulse laser. At the end of the wire droplet is created and droplet is filled at the interface. So, in this case the steps are like something like that: pressure pulse laser with the triple optical beam splitting. Actually the laser is divided into the three splitting beams, and normally Nd:YAG laser is used, and we use the wire feed system such that we target positioning system. So, we need to correctly positioning the drop at exactly at the interface between these two components supposed to join. Sealing gas assembly, that is a part of this system, and of course, mechanical positioning system, that is also to fit exactly that particular position of a workpiece. So, it starts with this thing first, droplet creation, then droplet detachment from the wire, droplet flight certain distance, and droplet land it, and then after landing the exact position and then solidification happens, then we can get the two joint. So, power requirement in this case, if you see the initially the droplet creation by melting, then move to this position, minimum power requirement, and droplet is detached, then power requirement is little bit more. So, with respect to time, this is the requirement of the power in the particular laser droplet welding. If we get the application of these things, the stainless steel, titanium and stainless we want to join of 2 micrometer thickness, but at the same time the gap between these two thickness is 2 micrometer gap. So, that effective that if there is a 2 micrometer gap between, it is a huge if we look into the scale of this welding process. So, therefore, in the micro scale when there is a gap is much more, so that gap can be filled by this liquid droplet, and this technology and methodology is called the laser droplet welding process. Even if other development also happened, that is called the laser spike welding. So, in these cases gaps in micro welding is problematic, definitely it is here also possible to joining the gap between these two components. So, in this case the joining, but in this case the normally we can do this thing in the lap joint configuration, and the lap joint configuration by spot welding, that is the principle of the joining of these two components. So, in the recoil pressure driven material flow to bridge the gap in the lap joint by spot welding process. Process is the melting using the low power in the upper layer. So, 2 layer in the conduction mode, try to put the keep the laser in the conduction mode, then sufficiently large or completely penetrated weld, completely penetrated weld had to be produced, then increase the laser power to generate sufficient recoil pressure such that diaphragm like liquid pull contact with the lower layer, such that it contact with the lower layer. So, therefore, adherence by the superficial surface melting or bridging like addition actually happens in these processes. So, in these cases lower surface clean, the surface clean is not good, then bridge like addition happen between these two component which are in the lap joint configuration, but there is a gap between these two joint. So, a lower layer is too conductive, then it is sometimes very difficult to join between these two components. So, application we can get the stainless steel of 2 micrometer thickness having the sufficient gap between the two set in the lap joint configuration. Of course, if we look into the other part, this laser droplet welding, actually laser droplet welding is mainly applicable for the butt joint configuration, but if you look into this laser spike welding, this is more applicable for the lap joint configuration. So, even in case of non-metallic materials, there is a advancement in the laser micro welding happens, that is called the twist technology, the transmission welding by an incremental scanning technique. So, in this case high beam quality laser like fiber laser, intensity is very high and easy degradation of the thermoplastic material, and if you use this thing in these cases that not exactly move the path straight way of the laser, rather fast rotating and the slow linear motion of the focused high beam laser can also be followed, such that different path can be generated, what has been shown in this figure. So, what are the benefits we can get, rather the some zigzag way to move the laser and or to design certain path, and one advantage is we can get that local and the temporal laser beam modulation strategy, you need to know these things. Dynamic periodic beam deflection is also applied to control the fusion and the solidification, mainly that is the purpose, and of course, the voids and the porosity can be reduced, or formation of distortion can also be reduced if we follow some kind of the zigzag path rather than the joining these two components following some single linear path. So, welding of the transparent polymers without any absorbing additives is possible to join by using the twist technique. Now, apart from this development in the micro welding processes, some development happens in the even called nanobonding processes. In this case, one is that diffusion nanobonding using the metallic nanoparticles. In this case, nanoparticles are sintered normally. We already discussed the bonding with the nanoparticles. In this case, nanoparticles sinter to form the networks of these networks are joined by the substrate, and it actually happens by the diffusion with the driving force to reduce the surface area. So, that is the driving force of these nanoparticles to join the components. With reducing the size of the nanoparticles, diffusion is enhances actually because of the low activation energy is required and increasing the specific surface energy. That results in the decreasing of the sintering and the bonding temperature. This is one of the advancement for the lowering the at the lower temperature the joining can also be achieved. So, this is the significant development at the low temperature joining processes for polymeric based microelectronics application. We can find out in the diffusion or solid state nanobonding. Direct joining of the carbon nanotube using the fused focused electron beam is also possible, and it also happens in the joining of the carbon nanotubes. So, for example, if we look into this figure, the single wall carbon nanotube of 2 nanometer in diameter crossing with another single nanometer tube CNT tube of 0.9 millimeter in diameter. So, 60 of irradiation of the promotes a intermolecular connection between the two tubes forming a junction. So, then electron beam is directed to induce the structural defect, because the even the single wall that the dimension of this diameter of this carbon nanotube is in the 2 nanometer. So, which is almost the size of the atoms in this case. So, at the interface creation of the defects is responsible vacancies or interstitial space such that these joints can be that it can join between these two components. So, self arrangement of the carbon atoms actually occurs at this high specimen temperature. Even nanosoldering and nanobrazing has been developed. If you see in there for successful nanosoldering or nanobrazing, tiny amount of the solder has to be precisely delivered to the bonding area. So, if you see this figure that assembly and the integration of the nanoelectronics in these cases. So, nanosecond pulse laser is used to melt the gold nanoparticles to bridge the platinum nanoparticles. So, here gold nanoparticles to bridge with the platinum nanoparticles, and very precisely we need to apply the gold nanoparticles. So, electron micrograph of the platinum and gold network that actually formed by laser bridging, if you see here, and schematic on the how platinum nanoparticles are held together by the gold, here it is given here. So, it is possible to development of the joining of these components in the even at the nanoscale, and that may be applicable in particular nano devices. Even fusion nano welding also developed. In this case, in case of fusion nano welding, the heat source can be used like the laser beam joule heating, similar to the resistance welding can also be applicable in these cases. Example is the welding of the plating nanowires. So, two nanowires are touched end to end. If you see the two nanowires end to end touch, and by piezoelectric manipulation, because only it is possible to bring these two nanotubes, platinum wire, nanowire, to bring together such that the interface and so piezoelectric manipulator is actually required. And after that, current is apply the current, and then it creates some resistance process. And the resistance nano welding we can see here, platinum nanowire to thin gold, where the resistance nano welding has been developed also. And but in this case, if you see the femtosecond laser with the application of the femtosecond laser, nanoparticles with the 100 femtosecond laser pulses is possible to join together in this case. Apart from that, here is the welding of the platinum nanowire before current supply, even here the application before current supply, and B to D, and the snapshot after 21 second starting of this thing. So that after application of this, the development of this joining of these two tube happens in this nano welding process.